Alright guys, so what we're going to do in this tutorial is a simple 3D truss analysis before next week we start looking at beams and doing a beam analysis. So we'll just open a standard model, and what this is, as I said, is going to be a three-dimensional truss. So we're going to look at how we both start modeling our trusses and then how we put it in 3D and join our trusses together. So the first thing, it's going to be made out of two frames, and then we're going to join them all together. So I'm just going to go into my parts and create a new part, and I'm going to call this my frame, and I want it to be 3D. I want to make sure I'm doing a a wireframe, and it's going to be planar, and I can hit continue. So it's going to be a square, so I just simply select the square tool over here, and it's going to have dimensions. Go to my dimensioning tool. It's going to have dimensions of 20 by 20. And it's going to have a cross brace across it, so it's going to have one member that goes from there and then another member which goes down to there. And if you want to stop it from continuing to offer you a new line, just hit escape. One thing we note that these two cross members, they'll be joined in the middle, but currently they're sort of separate members, so we just want to split one of those. And to do that, we can go over to the left hand side here. Whenever you see a little tool option with a little black sort of triangle down the bottom, if you just press and hold on that one, it'll offer you a few more options. So here, for example, we have auto trim, we have trim extend, and we also have split. So I just want to select the split one there, and basically I want to split this member using this other member. So what that results in is now I have this member split into two different members, but this one is still one member. Alright, so that's all we have for that one, and then we can hit done. Alright, and then we're just going to create another part, so I'm going to right click on parts again and hit create, and this will be my cross truss. And again, it's 3D deformable, it's a wire. We can create that, and this is simply just going to be a line which is 5 meters long. So here we're working in SI units, so my length for 5 meters will just be 5. Alright, and then I can zoom on that, so that's fine, and that's all we need to do for that one. Okay, so continuing to work my way down our model tree on the left hand side, I just want to create, they're all going to be made out of steel, so I'm just going to create a steel material model. So I can go down to mechanical. I'll give it Young's modulus of 210 GPa and a Poisson's ratio of 0.25. However, they're going to have different cross-sectional profiles. So I'm going to go down to create sections. I'm going to right click and say create section. So the first one's going to be my frame cross section. So it's my frame cross section, if I can spell correctly. And again, it's going to be a truss cross section, so I just need to make sure I select the right one. It's going to be made out of steel, but the frame cross section is going to be size of 6 by 10 to the -4 meters squared. And then we're also going to make one for the cross section, and again it's going to be made out of steel, but this one will be 2 by 10 to the -4 meters squared. Okay, and then we have to assign these. So at the moment you can see we're only looking at the cross truss, and if we go up the top here, we can see that the part we're looking at is the cross truss, and we can also look at the frame. So we need to apply the section to the frame. So if we go up here to assign section and select the whole frame there, we can go down our section list and choose the frame cross section and apply that. And hit done. And then we want to choose our cross truss, and we want to apply the cross section for that, which was the cross truss cross section. And we're done. So that's easy. Now moving further down, now we need to put all these things in together into one assembly. So if I just right click on instances and hit create, we can start putting these in. So we're going to need 2 of these frames. So I'll click on the first frame and hit apply, and that adds one in. And then if I click on the frame again, what you want to do is click on this auto offset other instances. So it just moves the second instance of this frame spatially, so it's not sitting on top of itself. And I can hit apply, and then we want 5 of these joining cross trusses. So just hit apply, select it, hit apply, select it, hit apply, and you can see they're being added up in there. So we need 5 total, so we need 2 more, and that's all done. 1, 2, 3, 4, 5, and then we can hit cancel. Okay, so if I rotate around, we can see now what we need to do is rotate these and get them in the right things. So essentially what we want to have is these 2 frames 5 meters away from each other, and they'll be joined up at the corners and also at the center node via these cross members. Alright, so to do that, the first thing we're going to do is, you can see that these cross trusses aren't in on the right angle. Alright, they're obviously going horizontally. We need them sort of going in the Z direction rather than the X direction. So to do that, we can go to the left hand side here where it says rotate instance, and we want to rotate all of these members. And then we need to select an axis we want to rotate it about. Now obviously we want to rotate it about the Y axis here. Alright, so it's so it'll be moved from the X into the Z axis, and it's asking us to select a starting point for that axis of rotation. So if I just select this top node here, I know that this line here is in the Y axis, so I can select that top node, and then I can select the bottom node, and then ask me for an axis of rotation, and I want 90 degrees, so I can do that, and it flips around 90 degrees. Now if I wasn't happy with that, if you get yours wrong, then all you need to do is just go back up to the previous step. But as we have it, ours is correct, and we can just hit OK. So all our trusses now, our cross members are on the right angle, but now we just need to join them up on the right spot. So we can go over to this translate instance tool here, and now we're going to translate this. So this one, I want to translate this truss to be down the bottom left here, so I can just select it and hit done. And then I want to move this node, so then it's coincident with this node, and that's how that works. So it's pretty simple, and then I can just hit enter. And then I want to move this one from this, I want to move this node to over here, and hit enter, and then keep, oops, sorry, I hit the wrong button there. I want to move that one from this position to this position, and then hit OK. And we just keep going through. So this one is going to move this node to over here, and this one's going to move this element from this node to over here, and this one's going to go in the middle, so I'm moving this node to the middle node over here. Alright, so now all our cross members are in place, and the last thing to do is to move the other frame into the position. So I just need to select my translate function again, select my frame, and so I can select any one of these nodes. So I can want to move this node, for example, over here. Alright, and now they're all in position. So we've put them, all our members now are in position, but Abacus doesn't yet know whether these, these members are connected at all. So the next step for us is really, or the next major step is for us to assign the joints between them, because they're going to be truss members, so they're obviously pin jointed. So we need to apply the pin joints. But just before we do that, we're going to create our load step. So if we want to go into steps and hit create, I'm going to call it my load application. And just for this one, we want a static general analysis, and I'm just going to change it to linear perturbation. So a linear perturbation is what we spoke about in class, where all the loads are normalized and we just apply a unit load. So just change it to linear perturbation here. And we're going to do that because this system will be in only basic equilibrium. So we hit OK there. Alright. Now, to set up our joints, to set up our pin joints, we need to go to, we need to change the module from the step module down to the interaction module. And you can see here we have all our interactions. So this is how we set up things like contacts as well as joints and things like remote forces, for example. Now, what we first need to do is we need to choose all the nodes which are pin jointed. So we're just going to create this wire feature here. So what this does is it creates a sort of an abstract wire between points. Now we don't have any distance between the points we want to select. So for example, down here in the bottom left, we have one node from our frame and one node from our cross member here, but they both have the same physical location. So we just want to select both nodes there. So to do that, we can just leave this as is and just go to the plus button. And you can see down the bottom here it says select first point. So if I just select the first point, and I also know the second point is in the exact same physical position, so I can just click again, and then it asks me to select first point again. So what you want to do is just go around the edge of this and make sure you click twice to select both points. Now Abacus is quite good in this, in that it doesn't let you select the same point twice. So you may select the frame as the first point, and then you will be selecting the cross member as the second point if you click. Now just make sure that when you click, so here it's saying select first point, right? And then if you go back and you misclick outside of it, it'll still say select second point because you haven't selected the second point. So you just want to make sure you get directly over it and then click again. So we should do this for all 10 joints. So we have on each side of our frame we have 5 connections, and we have 2 frames, so we're going to have 10 total joints. And then when we're done selecting all those, we can hit done, and you can see here we have 10 total joints. So you can see here when I selected, for example, that first one, the first point it selected was the cross truss, and the second point it selected was the frame, and then we kept going around like that, so we can see that that looks all good. Alright, so and then we can just hit OK on that. So that's selected all of our joints, and then we need to basically set up what type of joint we want. We can do that with the one above where it says create connector section. So this is going to be my pin joint, right? And if you just change it to basic. Now obviously with a pin joint, the deal with a pin joint is that the two nodes within a pin joint, they have no relative translational motion, but they do have relative rotational motion between the two. So we don't want any translational motion. So if you just go down for translational type to join, you can see here it says the constrained, this CORM value is the constrained relative motions. So it's saying U1, U2, and U3, which are obviously the translational motions are constrained. And we haven't set up any excuse me, rotational constraints, but for example, if I put in a cardan, an alignment one, then it obviously constrains the rotations as well, but we don't want to have that, so I'm just going to set that to none for our pin joint. All right. If you get a little bit confused, you can always hit this connection type diagram, and that'll bring a little thing here just to basically tell you what sort of connection you have. And you can see at the moment, yeah, we have that sort of ball and socket, that pin joint that we're looking for. All right, and then we can hit continue, and then you use this if you want to set up things like failure of a joint. So you can say at what loads that joint will fail, but we don't need that for this instance. Alright, so now we have the joints set up, and if we want to make sure of that, we've set up our joint, but we haven't said that the joins that we selected before have that sort of pin joint behavior. So now we just basically need to apply that pin joint section to those actual joints. So to do that, we go to create connector assignment, and it's asking us to select which set. And we've already set up that set, so if you just go down the bottom right here where it says sets, remember that was that wire set that we selected before, and we want to apply the pin joint to it. So we can hit OK, and then you can see it's applied that the joining connection, the pin joint connection, to all of those wire joints that we set up before. Alright, so that's looking all good. And last thing to do, well, a couple more things to do is apply our loads and then do our meshing. So the first thing is we're going to apply a load here. So I'm just going to go down to create, and I want to apply a concentrated force and apply it to this node and this node. So I'm just going to, click on one and click on the other. It's not working for some reason. There we go. And hit OK, and then we're going to apply a load. We're going to apply a load in the x direction of 2000 newtons and in the negative y of negative 2000. This member down here is going to be pin joined. So if we just go to the boundary conditions and create a boundary condition. So we want a pin join down the bottom there, and we want it to be a displacement condition. So I just want to select that member there, and so it's pin jointed, so it can't move translationally. And then this one, and then we're going to create another boundary condition, and it's going to be on a roller, and that's going to be this one here. And obviously on a roller, all it can do, well, it's free to move in the U1 and U3 directions, but we're going to constrain it in the Y direction, which is U2. Right, and then the last thing we need to do is now just create our mesh. So if we go down to change from load to mesh, now when you go and click on create the seeds, it's saying that we can't create seeds based upon the assembly. That's because when we imported them, we set it to be dependent mesh. So we need to do it by part. So if you just change it from assembly to part, and we need to basically mesh each part individually, which will then apply it to the assembly. So if we want to create our seeds, now obviously it's a truss, so we only want to have one element per truss member. So I'm just going to set the size to be 50. The seed size to be 50. I'm going to mesh my part, and yes, I only have one element for my member, and then I just want to set the element type. So I'm going to select that. It's going to be a truss, and I'm just going to make it a linear truss for the moment. And then obviously we just want to go to the frame, select the entirety of the frame. We want to again give it a global size of 50, so we only have one element per member. Hit OK. We're going to mesh the part. We have 8 elements being generated, which is 1, 2, 3, 4, 5, 6, 7, 8, so that's correct. And then we also want to set up the element type. So again, we want it to be a linear truss, so that's fine. And then when we look at our assembly, this truss will have 8 elements, the back truss will have 8 elements, and each of these cross members will each have 1 element. So that's how we mesh the whole assembly, by just meshing individual parts. And then we just want to go down to our jobs, go to the job manager. We want to create a new job, which is what we're going to analyze, and we'll just submit that. It's running. And it's completed, pretty easy. Now what we can do, if you just click before we go and look at the results, if we go to the monitor, and if you go to the message file, so this is where it tells you all of the sort of output concerns, and it becomes very useful in debugging. One thing to note down the bottom here is the solve times. Now Abacus is saying to us that it solved the total CPU time was 0.1 of a second. It only counts in increments of 0.1 seconds, so it's sort of probably less than 0.1 seconds. But if we had a bigger system and a bigger analysis, you can then use this number to sort of see how long your system is taking to solve. Okay, and we can close that off, and we'll just quickly have a look at the results. So, for instance, we can have a look at the stress, or we can have a look at the sort of the normal stress acting on our system. And as we can see, these blue members, they're negative. We'll just set up, change the font size so we can read it. A quick tip with that is if you just click on all of these and hit apply, it'll apply the same font to all of them. So we can see that these two blue members, these two vertical members here, they're blue, which is a negative stress, which is obviously compressive, whereas the red members are a positive stress, which is tensile. So then we can start to see which members are in compression, which members are in tension. All right, so that's where we'll leave it off today, and we'll catch you next week where we're going to look at conducting a beam analysis.